Very well, welcome everyone. So this is our very first lecture in differential equations. We're going to start by talking about what is a differential equation. Recall that in algebra, you dealt with a lot of different equations. In algebra, they had equations like x squared minus 2x plus 1 equal to 0. But this is an equation. You have some expression on the left-hand side, you have a constant on the right-hand side, and you have equality. Well, remember that the goal of presenting an equation is to solve that equation. So this is the goal. The goal is to solve the equation. So this is algebra. When it comes to differential equations, we are dealing with equations involving the derivatives. So let y be a function of x. X is a free variable, independent variable. X is independent. Depending on the domain that you can define x on it, y depends on x. Dependent. So if you have y equals to f of x, you can define a differential equation in y. Let us write this guy down here. A differential equation in y is an equation. In this equation, you have x, you have y, and the derivatives of y. This equation contains x, y, and the derivatives of y. So now I expect you to ask, what if I have a function in x? So a quick note for you. If x is equal to g of y, it means that x depends on y. In this case, x is dependent and y is independent. Then how do we define differential equation in x? A differential equation in x is an equation containing, well, in this case, you have your y, x, and the derivatives of x. So when it comes to differential equations, it's important for us to distinguish what is the independent variable. So a differential equation in y and a differential equation in x. Of course, we can represent other variables as independent variable as well, like t, u, v, and so on. So very well, when you're talking about differential equations, you're either dealing with ordinary differential equation or partial differential equation. We learned about both of them in calculus. Let's go over some examples. Ordinary differential equation. Or ODE, and partial differential equation. Or PDE. Now, an example of ordinary differential equation is y prime plus 5y equals to e to the x. An example of partial differential equation, remember the Laplace equation or other equations involving the partial derivatives, like the second derivative of u with respect to x plus the second derivative of u with respect to y equal to 0. As you can see, here you're dealing with the partial derivatives. That's why we call it a partial differential equation. Another example of ordinary differential equation, here you have the second derivative of y with respect to x plus the first derivative of y with respect to x plus 6y equal to 0. Ordinary derivatives, dy over dx. Another example of partial differential equation, well, here we have the second derivative of u with respect to x is equal to the second derivative of u with respect to t minus 2 the first derivative of u with respect to t. Partial derivatives, and you have an equation, so partial differential equation. The question is, well, why differential equation is important for us? What's the reason that we are interested in differential equations? Well, suppose you have a friend. Your friend is in biology. Well, he's mentioning that they have a case study about population of frogs, of fish, or some organisms. And in that case study, the rate of birth and death is constant. And they notice that the time rate of change of population is proportional to the population itself. He asks you, well, you're the mathematician. You know about the derivatives. How do I model that case study? So in a biology case study, there is a case that the time rate of change of population is proportional to the population itself. And consider the case that the rate of birth and death are constant. What's the mathematical model? It means that how do we formulate this biology case using math? Well, let's read this case study. What do we have here? The time rate of change of the population. Rate of change of population with respect to time. So of course, I need to come up with a population formula. What is that formula? I have no idea. So let us call population P of T. P of T representing the population. I don't know what that is, so I'm just going to call it P of T. Rate of change, it means that I'm dealing with the derivative. The derivative of population with respect to time. So the derivative of population with respect to time. It says it is proportional to the population itself. Proportionality, it means that it is equal to a constant like C, like K, any constant that you like. K times P of T. K is the constant coming from algebra. Or another representation is P prime of T is equal to K times P of T. This is the mathematical model for this biology case study, and the next step is for us to solve it and present the population formula. Next, we learn how to solve it. Very well. So when we have a differential equation, we are interested in associating some characteristics, some properties to that differential equation. First of all, let us talk about the order of a differential equation. Definition of the order. So the order of a differential equation is the order of the highest derivative in that equation. And note that if y is equal to f of x, so of course x is independent variable, free variable, and y depends on x, then the general form or the normal form of a differential equation of order n is denoted by, well, in this case, we are connecting x, y, and the derivatives of y using a relation like f. F of x, y, the first derivative of y, the second derivative of y, and note that since the order is n, it means that the order of the highest derivative on y is n, y, n equal to 0. Let's put this guy in parentheses so you know that we're talking about the order of the derivative. So again, what is the order? The order of a differential equation is the order of the highest derivative in that equation. And in general, if y is equal to f of x, then the general form, the normal form of a differential equation of order n is written this way. It means that you are connecting x, y, and the derivatives of y using a relation like f. Give us an example. What are you talking about? The following are examples, ordinary differential equations. The first one, let's take a look at this guy here. You have y minus x plus 4 y prime equal to 0. 2. You have y minus x dx plus 4 dy equal to 0. Another example. The second derivative of y minus 2y prime plus y is equal to 0. And the fourth one, the third derivative of y with respect to x plus x times the first derivative of y with respect to x minus 5y is equal to e to the x. Okay. Let's see what do we have here. So here you have a relation between x, y, and the derivative of y. This is a differential equation, and the order is equal to 1. The highest order of the derivative is 1. Well, what about this guy, the second one? I don't see the order of the derivative. What I'm going to do, I'm going to divide up everything by dx. So divide by dx. So if I divide by dx, y minus x dx divided by dx is y minus x plus 4 dy over dx. Okay, I see the first derivative here. Equal to 0 divided by dx is 0. Well, the order, as you can see, is 1. The derivative is dy over dx. So the order of this differential equation is also 1. N is 1. We call that dy over dx is equal to y prime. What about this one? We see a relation between, well, the second derivative of y, the first derivative of y, and the order is 2. The highest derivative appears here is 2. So n is equal to 2. The order of the differential equation. Now, number 4. Here we have a relation between the third derivative of y, the first derivative of y, and a function of x. Well, as you can see, the highest derivative has order 3. So the order of this differential equation is 3. N is equal to 3. The order is 3 because of the third derivative of y with respect to x. Very well. So we talked about the order of a differential equation. Now we're going to classify differential equations based on the linearity. We can divide up differential equations if they are linear or nonlinear. Later on in this class, based on the classification of the differential equation that we have, we're going to present different methods solving those equations. So linear ODE definition. Let y be equals to f of x. An nth order differential equation like f of x, y, y prime, the second derivative, the nth derivative equal to 0 is called linear if we can present it this way. So a sub n x, the nth derivative of y. You have an expression in terms of x times the nth derivative of y plus another expression in terms of x, a n minus 1 x times the nth minus 1 derivative of y plus, as you can see, we are forming a linear combination. A sub 1x times the first derivative of y plus a sub 0x times y equals to, well, a function in x, like g of x. So you can say that if f is linear in y, if f is linear in y, y prime, the second derivative, and the nth derivative of y. Or in another word, you can represent this relation this way. So you have an expression in x, another expression in x, these are all multiplied by the derivatives or the y itself. Well, so what is our observation here? The observation is that we don't see any multiplication of y and its derivatives. So let me write down this quick note for you. Note. In a linear ODE, we don't see terms like y times y prime or y times other derivatives, or we don't see like the terms including y, a sub n y times the derivatives, or multiplied by y or anything else. We don't see for example, the derivative raised to some exponents, y prime raised to the second power, or in general, the derivative raised to any other power greater than 1. So this way you can distinguish between linear and non-linear ordinary differential equation. Let's go over a quick example for you. So in this example, here we have 1 minus y times y prime plus 2y equals to e to the x. Let us compare this differential equation with a linear differential equation. Does it satisfy the definition of a linear differential equation? Let's take a look at the first term here. Here you have an expression in y multiplied by the derivative. Well, next to the derivative of y, you must see an expression in x, not y. So this is the red flag because of 1 minus y times y prime. It is not linear. So this guy is not a linear differential equation. The second one. Here we have the second derivative of y plus sine y equal to 0. Compare this differential equation with a linear form. I have the second derivative. I don't have any problem with the second derivative. I'm good here. But here I have sine of y. If it was just y, I'm good with that. But because of sine of y, cosine of y, e to the y, a function of y, then its composition of y, then this is a red flag. Because of sine y, it is not linear. Another example for you. Number 3. Well, here we have the fourth derivative of y plus y squared equal to 0. Okay. So the first term, it's good. It's just y to the fourth. The expression next to y to the fourth multiplied by y to the fourth is just 1. We don't have any problem with that. When we move to the next term, it is y squared. Again, if it was just y, then you're happy about it. You don't have any problem with it. But since it is y squared, because of this term, it's not going to be linear. Because of y squared, it is not linear. So note that when we are talking about y to the fourth and y4 in parentheses, there's a difference between them. This means that, hey, you have a variable, you have a function like y, and you raise it to the 4. It means that you have y times y times y times y. But when you see 4 or any number in parentheses, it means that we take the fourth derivative of that variable of that function. Take the fourth derivative of y. That's the difference between these two. So when you see, for example, y squared, it means that it is just y times y. But when you see y prime, then y double prime, It means that you are dealing with the second derivative of y. It's the second derivative of y. So for simplicity, instead of writing y raised to the second in parentheses representing y double prime, I just write it this way.